Thank you very much, Lars, for the kind introduction. I'm very happy to be here. I started here at TU Dresden about 1.5 years ago, and I'm very happy about this. And as Lars mentioned, a few years back, we were very busy. My background is in physics, like Lars mentioned, but very early on, like starting around 20 years ago, I became interested in modeling infectious diseases. At that time, it was kind of a fringe science and, a small community of people trying to understand how pandemics work and anything related to the global spread of infectious diseases. And then a few years back, suddenly we moved from the fringe into sort of the center of attention, and everyone became interested in our work, which was an exciting time. And would like to give you a brief overview of how we, among other groups that are dealing with this, are trying to get a better handle on events like the COVID pandemic or coming pandemics. So I'm going to start with this little illustration, which is a sort of data that displays the dynamics of the COVID pandemic during the first few months. And the only take-home message you can really extract here is that it's very complicated and dynamic. The numbers go up and down, the incidence, and it's spatially very incoherent, except for in the very beginning when the virus emerged and it very quickly spread across the globe. And then over the course of 2 years, it went up and down. It's very complicated. And it is in part, in the bigger picture, one phenomenon that is complex and is a member of a family of crises that we have to be dealing with, like political polarization, the loss of biodiversity, and other things. And all of these phenomena share, in a nutshell, a number of features. Typically, they're multi-scale. That means they evolve on multiple time scales, on multiple spatial scales. In case of a pandemic, it happens in our contact networks. If it were to spread in this room, our contacts play a role, but then it also evolves and, does its thing on a global scale. They're typically networked, like the pandemic occurs on contact networks, but also on global mobility networks. So understanding networks is important if you want to understand this phenomenon in a holistic way. And they are nonlinear. There are certain feedback mechanisms that play a role. For instance, it's just not a virus that passively spreads in a human population, but we react to it. We start wearing masks. That means the incidence goes down, and then we stop wearing masks and the incidence goes up. So there's a very strong feedback mechanism in these phenomena, and often many of these phenomena, like pandemics or climate change, they interact with one another. So how can one go about understanding these phenomena? This is something I just mentioned earlier. Many of these crises are interconnected, so it makes little sense just focusing on one and extracting it from the whole and hoping to understand it without accounting for all the other things that may play a role. So I alluded to this earlier. If you want to understand a pandemic or infectious diseases that spreads across the globe, there are multiple levels, on which you can try to tackle the problem. One is, for instance, understanding how a virus spreads in a population of individuals, in a network of individuals. To understand this, you have to understand the shape of our contact networks. We're not a well-mixed population, or this contact structure plays a very important role. And it is kind of a shame that we know very little about how our contact networks work. What is their structure? That's just a beginning. We're just beginning to understand these, and I will come to a number of technologies that we use to understand these better. And then on a very different level, mobility networks play a role. On the left here, you see an illustration of the worldwide air transportation network that I will also discuss in more detail. And that structure obviously has an impact on how things spread on a global scale. So let's get back to this video that is just kind of so complicated because underneath is a very complex mobility network that does this. So how do we do this? If we go back in time, one way of understanding this, what's happening today, is making a comparison to how pandemics spread, say, a couple of centuries ago. The most famous example is the Black Death, 14th century. It was also a pandemic on the European continent, and it crossed the continent in this wave-like pattern, starting in the southern Europe, and it just sort of propagated at a constant, frankly, a constant speed of a few kilometers per day on average, and it, crossed the continent in a matter of a couple of years. So it's this kind of wave-like pattern. And in fact, if you look at the literature, the first people that try to understand this, they try to devise mathematical models that are of the reaction diffusion type that had these constant wave propagating waves as a solution, and they try to explain it this way. And it's kind of intuitive, obviously, because like a couple of 100 years ago, almost all traffic or human mobility was dominated by local mobility, people going from one village to the next. Of course, there was also long distance traffic, but not as much as today. And this combination of local dispersal and local proliferation generically leads to propagating waves. In fact, you can ask a student to, cook up a simple agent-based model here on a two-dimensional lattice where little pixels can infect neighboring pixels, and generically what you get as a solution is a propagating wave. It's a little random on the edges, but in a nutshell, generically it leads to a propagating wave with a constant speed. And that would be a model for the pandemic a few 100 years ago. And the good thing about simple patterns like this is if it were like this and we would have an outbreak somewhere, obviously we could just measure the speed of the wave and then predict at what time the wavefront hits a certain location. That's a good piece of information. If something is happening, you can predict when it reaches you and you can prepare yourself. But just in the simple, super simplified computer simulation, if you make one little change and you add very rare long-distance mobility events, you get the image on the right. So every now and then a person, or in the computer, the pixel infects some other remote location, and just qualitatively, the pattern looks very different. Now, you may say, well, that's what I expected because that's, how the model is constructed, and it's true. But it has an impact because, if it's more like the pattern on the right, which is computationally just as simple, it is very hard to pick out a spot in the picture and predict when it's going to get to you. So that information is lost. And that's how things are happening now. This is a very old 2009, one of our earliest computer simulations that we made for the H1N1 pandemic in 2009, where we took the global air transportation network, which was very difficult to get at that time. We kind of scraped it off the internet, which was an adventure. And we put it into a computer simulation and ran a simulation for the H1N1 pandemic. Now, I'm not going to go into this so much. I'm just showing you this video to see that initially it may look like a wave, but if you take a snapshot like this one, there is no wave because the air transportation network has these long distance connections and everything looks like a spatio-temporal mess. So it's very hard to say when the pandemic will arrive at a certain location. And in fact, that's why we devised these computer simulations in order to make these kind of predictions. And as I said, the core of this kind of modeling is the air transportation network, like this network here. It's a full network. And just to get sort of an intuitive idea of what travel on or traffic on this network means every day humanity travels the distance that is equivalent to 3 times the radius of our solar system on this network alone. So there's, huge traffic volume happening on this. And obviously it has an impact on how pandemics spread. And we just experienced it a few years back in the COVID-19 pandemic, the speed at which this is happening. Now, way back, this is about like 12 years ago, we tried to understand this phenomenon better. And one of the things that we did back then is we said, okay, is that really the case? Is the air transportation network really removing the predictability that formerly was derived from just geographic distance? And you can see this, it's an old paper, so COVID-19 isn't in it yet. So it was still fringe science back then. And when you look at the scatter plot of like taking an outbreak location, like during the H1N1 pandemic, and then you just illustrate the arrival time of that pandemic at a certain location, you get, a correlation. But it's very hard to just take geographic distance as a predictor for the arrival time, obviously, because this air transportation network is just sort of globally connecting us. That's just sort of a quantitative assessment of what I just explained to you qualitatively. And so, in fact, back then, and basically starting like around 2003, 2005, people thought, well, so what? We have all this data, so we can just collect data on human mobility, plug it into, write down a mathematical model for it, plug it into a big computer and just, crank it up and run the simulations. And that's what you do. That's one way of doing this. And this is one way of, taking a tool, a computational tool, and making predictions. And it's a valuable tool, but it's not the only way to approach this. And we kind of have this dilemma also when we talk about AI, which is another tool, which is super powerful. Sometimes I say in my presentations that AI is a tool for predicting things that we don't understand. And complexity science, which is where I come from, is kind of complementary to it. It's about understanding things we can't predict. And bringing these two sides of a coin together is really a challenge at times, but it's also very valuable. So is this the only way of dealing with this? Is it really so much more complicated nowadays? And do we need this? So around that time, around 10 years ago, I had this idea, what if we think about a pandemic not from our own perspective, but rather from the perspective of a virus? So we're used to looking at the globe and these maps, and we can make these illustrations of the global air transportation network. We see the different countries and everything's connected. But what does the virus see? Now, a virus is not super smart in a lot, well, there are different ways to think about this, but imagine you're a virus and you're on a host, say, a person that is at JFK in New York. Now, obviously, places like London and Heathrow are very far apart. It's a long distance. Smaller airports like in Pittsburgh or in North Carolina are closer, but there's less traffic to these airports. So what if you can translate traffic flow into some sort of effective distance? So from the virus perspective, because there's a higher likelihood of you being transported to one of these European hubs, the virus sees it like this, okay? For the virus on the host in New York, these places, the hubs in Europe, are closer, and these smaller airports in the US are further apart. If you find a way to translate the probability of ending up in a in some destination location to some sort of effective distance, and that's what we did back then, it's actually not a new idea, it's quite old, but we applied it in this scenario. So here's a little video of the traditional way of looking at things. But if you look at this, taking, say, Wuhan as a starting point, and you display it in this effective distance kind of scenario, where now the radial distance in this illustration is this effective distance. And you can take any location sort of as a starting point. That will tell you a bit more about how a virus spreads. And that was the hypothesis. So maybe we just have to redefine the notion of distance in this context of pandemics and look at the phenomenon again. So here are two computer simulations. They're sort of fake pandemics, where you see on the right the traditional view of it. You just run the computer simulation and you look at it. It looks incoherent in a sense. And on the left, you see exactly the same computer simulation, except for you're displaying it in this effective distance framework. And you can see that what looks complicated on the right looks like, again, sort of a propagating wave. And that told us back then, well, the phenomenon isn't so complicated, actually. It's still a spreading wave. It's just that you have to redefine the notion of distance. Now, that's not so only an academic sort of insight, because it can be used to make actual predictions about when a pandemic will arrive at a certain location. Because you can just run it, on the left, and then you can see, at that point, the wave is approximately going to hit that location. And in fact, if you take the same illustration that I showed you earlier and just replace the geographic distance to the outbreak location by this effective distance, mostly everything collapses onto this line. So that's good, because that means we can now make predictions even if we want to avoid running massive computer simulations that take a lot of time. So it's actually quite simple. Now, given that this is a keynote, I will tell you a little bit more about this paper, which is something I did, and I regretted it for a little while. But it's entertaining, so I'm going to entertain you a little bit. When we published this in Science back then, shortly after, this is the paper, after we published it, I got a message on Twitter, nice work, very impressed by your accuracy in predicting H1N1 outbreaks in Zamonia. Does anyone in the audience know where Zamonia is? No? Does it ring a bell for someone? Some people? Okay. So here's the story, and I encourage you not to repeat this. So there's a figure in it. This is sort of like the result figure that I showed you earlier. And when you look at this, there are all these countries, arrival time versus geographic distance. And there's this country, Zamonia, in it. And I put it there. And then a while after the paper was published, I get a letter, an email from Science. Dear Dr. Brockmann, regarding your recent paper published in Science, we've received notice, very anonymous, that figure 2D describing the spread of H1 influenza contains the nation of Zamonia, along with better known countries such as France, Spain, India. It's British humor, I love it. So this dryness. This would appear to be an error, as to my knowledge, no such country exists. Based on the countries in figure 1E, I'm wondering if you meant Latvia instead. If necessary, we'll publish a correction. And so I responded, Dear Harry, thanks for getting in touch. Let me ask, did you try to Google Zamonia? And then it continued. The reader who submitted this letter writes, not having heard of Zamonia, I looked it up. Zamonia is a fictional country in the fantasy novels of Walter Mörs. Those of you from Germany may know him. He writes very funny novels. When I Googled Zamonia, I could find nothing more informative than this. And so, in fact, it is true. It's from, entertaining books. And I put it in this figure because I wanted to see if my co-author would recognize it. He didn't. And then I figured he didn't see it. So we're going to submit it and I'll see if the referees see it. They didn't see it. And the journal also didn't see it. So I figured I'll leave it in there and see what happens. And then the editor at Science sent me a note, only partially. I will show this to you. It starts with, "This is unbelievable." And then she went on like, how could you do that? And blah, blah, blah. But we're friends now. And like only a year later, she thought it was also funny. So if you ever publish a paper with me, you have to be very careful and look at every figure. But I'm not going to do this again because I was still in my early stages of the career, and I was a little afraid that this would backfire. But the person who found it said, "It's really funny and it's fantastic to pull this off in science. I don't think the entertainment detracts one bit from the work being serious at all. Definitely count me in as an ally. I've yet to plant something on the sort of in my own paper." So that might be a side effect that you will find other things like this. But I've been reading his papers and he hasn't done it yet, or I haven't seen it. So that's on the funny note, but we use this technology or this idea of effective distance and making predictions about arrival times, obviously, when the COVID-19 outbreak occurred. So initially it spread in China. And you remember that very early on, there were cases everywhere in the world. And it was important for us to be quick on making predictions when a virus would arrive at a certain location with a given probability. And this is what we did early on in our work in the pandemic. We tried to estimate arrival times based on the state of affairs. So that was very practical in a sense, and people used this sort of technology. And very quickly, we realized we need to understand this phenomenon better on another level. And I mentioned this earlier. The pandemic is not an event that sort of passively spreads through or covertly in a population that is unaware of it. Obviously, we, as the host, reacted to it. And that's the feedback mechanism. Like the virus spreads, we start wearing masks, or there's, interventions. And that then sort of dampens the spread of the virus. When that happens, we become more relaxed and the virus spreads again. We were able to analyze the data, how many people go from one zip code to another, and observe this as a function of time. And we wanted to understand how this changes, how massively it changes, and how it, say, goes back to normal, etc. So during the first wave of the pandemic, we just sort of made maps. You could click on them and see, in my county, the mobility changes this way, etc. And it just went down, obviously, because of all the containment measures, etc. But what was interesting, so this is like the first months of 2020, and you can see sort of the mobility at a sort of baseline level, and then there were like these containment measures by the federal government, or like Chancellor Merkel at that time gave a speech and said, the situation is serious. And then within like a few weeks, mobility went down by roughly 40%. But what's interesting to observe is that after the first wave, mobility went within like 2 months back to a normal baseline, even though there were no sort of explicit lifting of the containment measures was going on. These are the green lines. So we measured the first trend of the human population going back to their normal state, despite the fact that the situation was still serious. So that was kind of this. We wanted to use mass data to understand behavior. And we kind of also wanted to understand on a quantitative level what that change in behavior meant to the typical dynamics of a pandemic. At that time, there was a lot of discussion in the media about like flattening the curves. So this is sort of a toy example of a pandemic or like an epidemic that spreads in a pre-lockdown network compared to one that is locked down. And you can see it's sort of broader and flatter and less is happening. And that was kind of sort of a proof of concept of how much you can achieve by this behavioral change. And another element that we did back then, and it's kind of again a digression, is using this mass mobility data to understand mobility, say, on an urban scale. And how can we do this? What you see here is when I still live in Berlin. I'm actually moving to Dresden in a few weeks. But this was back then. This is where you see my home and where I worked. And the green, the red stuff is where I move. And you can, download this at Google, your Google data that is being collected. And a postdoc of mine asked me, give me your data and I'll make a picture. And that's what he did. And to understand what is happening, say, with a pandemic on an urban scale with, public transportation, lots of people like on the subway, and a high density of individuals, etc., it's important to understand this kind of structure. And it's very complicated. Everyone can generate an image like this. If you have the tools, the data is there. But what Ben, my postdoc back then, did, he tried to also simplify this picture a little bit. And you can see it just by a little bit of a transformation. So here's a little video that he made. To me, it's a piece of art. That's Ben Meyer's probability of being somewhere in Berlin. And I don't understand why it doesn't start. Maybe I have to press the button again. Yeah, here we go. And so you can see like a generic map of Berlin, and in the top right corner, you see the time of day, and you can see it changes. But a map like this isn't telling so much. But if you do a density equalization, so you expand the regions where the person stays a lot and shrink the locations where he's not, you get a very rhythmic heartbeat kind of. It almost looks like a heart, actually. And you can see that it's actually quite simple. Everything is dominated by being at home or being at work. He spends a lot more time at home in Treptow. And you can make this for every person. That was kind of an art project that he did. But this kind of information, the redundancy in mobility in an urban scale, helps us understand the spread and dynamics of infectious disease on that scale also. Now, having talked about mass data so much, there's another element which becomes more and more important in understanding infectious disease dynamics, but even beyond that in the public health universe. Also in April 2020, we started the Corona Data Donation Project. The idea was this. It's again about monitoring, just like with the mobility monitor. In the beginning, we had an issue about just measuring the incidence. You may remember that people had to report when they had an infection. The numbers had, a gray area. It was very hard to actually measure the state of the pandemic. Nobody knew what was going on because people there were no tests, etc. And so we figured maybe there's another way using digital science to measure this kind of thing. And that's why we started this project. And the idea is quite simple, based on a paper published like a year before we launched this. We figured in Germany at that time, around 10% of the population were wearing a fitness tracker or a smartwatch. And these instruments, they measure heart rate, step count, and sleep. And the paper that I mentioned, they showed that if you take a population of people that wear such a device and a bunch of people get sick, that, typical effects of a respiratory disease like COVID-19 is you get a fever. Fever means your heart rate changes, your resting heart rate. You move less and you sleep differently. So maybe, just like with Google Trends, if you take a large population and many people donate this type of data, we can measure indirectly by just looking at how many people have a weird heart rate consistent with a respiratory disease to measure the dynamics of COVID-19 in real time. Because when people donate their data on a daily basis, we can see it. So that was the idea. It was much harder to actually do this. But we launched it, and within a week, 500,000 people joined and donated the data that was collected on the wearable devices on a daily basis. So they had an app on their phone, they registered, and like all the data came to us. And we have around like 180,000 people stayed active, and more than 100,000 people donated data every day over the course of more than 2 years. And you can kind of see in these time series, this is a person that had an infection where the red line is, and you can kind of see it changes in a very typical way, all 3 data traces. And so one of the things that we started first was to measure the incidence indirectly using this data. Along with colleagues in the US, they did the same kind of thing. They had like around 30, 40,000 people participating. And after a while, we had the algorithms right to measure this incidence indirectly and correctly until around April of 2022, where it stopped working. And the reason was not because the devices stopped working, but rather the numbers became wrong because people stopped testing, they stopped going to the doctor, etc. So that was the idea, to have like a citizen science project where individuals donate data. It's not a representative group, obviously, but to understand it better in real time. And it turned out that this was sort of a valuable data set because, as you remember, there was the pandemic, and then slowly this whole concept of long COVID came about. People, were developing these symptoms that didn't go away. And that no one had this on the radar first. And so one of the first, and it was also controversial, some people saying, so it's psychosomatic, it doesn't exist, people imagine this stuff. Now it's established. But back then we figured maybe we can just look at the whole population and see how long a heart rate, say, is affected by a COVID infection, because later on during this, we were also running surveys with the same app. So we asked people, when did you get an infection, etc. And we were able to see, and this was like the first sort of long and post-COVID evidence, that on average, and this is an average, even 80 days after an infection, the resting heart rate of a person is still not back to baseline. And that means that for most people it's okay, but some people have a very long recovery time. And then there are other elements that we don't understand yet. We see this, like one of the first maps that we did, I told the people, make a map of the heart rate in Germany. And then my students say, oh, you always want to see maps, you always want to see maps. And I said, yeah, maps are cool, you can see stuff in them. And so we found that like the resting heart rate, and we still don't know why this is, we tried many things, is higher in the eastern states than in the western states. I still have no idea why this is. We also found that in the second, and this is sort of systematic, this is not an error or anything, in the second year of the pandemic, the resting heart rate was higher than in the first year, potentially because people changed on the population level their behavior, maybe gained a little weight or something, whatever. We don't know what's going on. We still don't know. But this picture is like 5 years old. Another element that we're looking at is sleep. And so it's not related to COVID at all, but it is within this data. We are trying, made a sleep map of Germany, and we're trying to understand how sleep works in urban areas and non-urban areas, and how this correlates with the sun, etc. This is sort of work in process and in progress. So there's, what I'm saying is you start a citizen science project with a certain aim, but there are all of these other questions that you could potentially answer or not answer, like with the Pulse of the Nation. So with this, I'd like to end this by thanking the team that we're setting up here at the Center Synergy of Systems in Dresden, and that did all this work. So thank you very much.